So welcome everyone to your 2.2 lesson, and this is on the factor theorem, which closely relates to 2.1. So if you're stuck on 2.1, make sure you go back and get caught up. So I'm going to give you a chance right now to copy this. So if you want, you can pause the video, and then we will go through these three definitions. Okay, so similarly to 2.1 with the remainder theorem, when you were to substitute in the value that you had, so for example, if you were to factor x minus 2, if you were to sub into your function the value of 2, this will give you the remainder for that function. So in the factor theorem, if you're going to factor out x minus b, or for example, if you're to factor x minus 2, and you're substituted into your polynomial function, if it is a factor, meaning it'll factor perfectly, the remainder should be 0. And this is what the factor theorem states. Or similarly, if ax minus b is your factor, then if you were to substitute b divided by a, the remainder should also be 0. Now noting that a in this situation cannot be 0. Now, the integral zero theorem and the rational zero theorem are very similar. The only difference is that in the integral zero theorem, the coefficient is 1, like this polynomial here. The leading coefficient here is 1. And the rational zero theorem, it has a factor where the leading coefficient is something other than 1, as well as the constant. So what the integral zero theorem means is this is your polynomial. If you are trying to figure out what you can factor this by, because ultimately we are trying to factor this polynomial. And if you're trying to figure out, so what am I going to do? X minus 1, x minus 2, x plus 1. These values that you are trying here, you can actually estimate or find from looking at your constant term. So any factors of the constant term, so plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Any of those values are the 4 values that you would try first when you find that factor. However, with the rational zero theorem, if you are looking at something that has a coefficient other than 1, then the b value in your ax minus b is a factor of the constant term, so plus or minus 1, plus or minus 2 in this example, and the a in your factor here is a factor of the leading coefficient, so this would be plus or minus 1, plus or minus 3. So an example might be negative 2 over negative 3. So you take one of these, this is your b value, and you take one of these, and this is your a value. Or if you were to write this, it could be 2x minus 3, or negative 2x minus 3. Different combinations because you have plus or minus. So we have to figure out which of the following factors are actually factors. So we're going to use the factor theorem. This is one option. Another option, though, is you could have done the long division and have noticed that the remainder was 0. So if we're going to solve this, you would set this equal to 0. So that means that x equals 2. So we're going to take this p of x and we're going to substitute in 2. So we're going to do 2 to the power of 3 plus 3, and so on. And you'd end up with 20, and then you'd again do the same. So you have x equals negative 2, and you'd be substituting in p of negative 2 into your function. And as you can see, when you end up with the remainder being 0, x plus 2 is a factor of this polynomial here. And you can see that you could have used the rational zero theorem to use the factors of a and b to come up with this 1x plus 2. Now we're actually going to try and factor this fully. So the examples yesterday we were told what the factors are. Here we have to figure out what the factors are. So we're going to use the factor theorem, which says that we're going to see this here using the integral zero theorem as well. Since it's 1 and negative 6, these are all of the possible factors that we could use to try and factor this fully. So I've already tried a few. Negative 1 gets 0. You could have tried multiple. You could have tried negative 2. However, that got 4. So using the factor theorem, we know that this is one of them. Because we substituted in x minus, we substitute x as negative 1, when we're actually solving for the factor, we have to put it in as the opposite. So we're going to divide x plus 1 out of our polynomial x cubed plus 2x squared minus 5x minus 6. Now this process is what you've done before, so I'm going to pause it, solve for it, and you can check your solution once after you've paused it as well. And so here you've seen in the process along the way, I factored, got the remainder of 0, which is perfect. And so what we're left with is we have x plus 1, which we knew was a factor. And we also have x squared plus x minus 6, but we were asked to factor fully. So we want to take this even further. And then this is just a quadratic. So we know that it is x plus 3, x minus 2, two numbers that multiply to get negative 6 and add to get that positive 1. And there you go, you factored fully. Now we just finished that example, and I'm going to show you another strategy. So previously we were doing long division for our polynomials. So we were trying to factor, and the one way we knew was long division. I'm going to show you another way, and this is called synthetic division. Some people say it's faster, but whatever you prefer is fine. So I've already written some steps here, so I'll give you a chance to copy them. So I'm going to scroll down so you can copy those steps out, and then we will start the example. So since this is the same question from before, we know that x plus 1 was a factor. Again, you would do the same process. You would substitute in values. So using the integral zero theorem, you'd substitute values into this equation here and figure out which one's factored. So in the synthetic division, here's your template. You have your box up in the corner there, and you're going to be, in this case, you're going to be subtracting. So what you're going to do is you're going to take the number from your factor, so as is, not doing the opposite. You're going to take it as is, and then because you're doing that, you're going to be subtracting in this situation. Then step 2 is you're going to take all the coefficients and you're going to put them in a row. So our first coefficient is 1, and then 2, and then negative 5, and then negative 6. If we happen to not have this term, we would have to put 1, 2, 0, negative 6. You have to always put something in place of that term. If you didn't like doing it this way, you could have done it another way and had your box. And what you would have done is instead of keeping this term exactly as is and subtracting, you would do the opposite. So you would do negative 1, and then you would be adding. So I'm going to stick with this way up here. But again, it's completely up to you, your call, which way you prefer. So first step is to drop your first term down. And then what you're going to do is you are going to multiply your box number by your first term that you've dropped down. Once you've multiplied that, then you put that answer you get up here. And again, we said that we were subtracting. So you go 2, subtract 1, and you get 1. And now you do 1 and you multiply it by your box number, which is 1 times 1, and you get 1. And you do negative 5, subtract 1, and you get negative, I'm going to switch colors, and you get negative 6. You go again, take this bottom number, negative 6, times it by your box number, which is negative 6, and then you do your negative 6 from up here, minus negative 6, and you get 0, because a negative and the negative make a positive, you end up with 0. Now how you write this as your final statement, what you should notice is down here, these are all the coefficients. So you take this back as your factor, which was x plus 1, and then you go with these as your coefficients, but you go 1 degree less than what you started with, because we've already factored 1 out. So you know it's x squared, so 1x squared plus 1x minus 6, and then again you would factor just like we did on the last page. So that's using the factor theorem, considering the integral zero theorem and the rational theorem. If you have any questions, please make sure you message on the class site, and hopefully I'll get back to you as soon as you can. And have fun factoring.